So here we've got a random variable x, which is distributed with a uniform distribution between -3 and 5. And what that means is that there is an equal likelihood of x taking any value between -3 and 5, and there's a 0 probability that it'll be less than -3 or greater than +5. In order to write down the probability density function of this random variable, we need to consider three parts: the part where x is less than -3, the part between x being -3 to -5, and the part where x is greater than 5. So our probability density function, if x is less than -3, there's a 0 probability of getting it, and there's a 0 density. The height of the probability density function is just 0, and that's for x less than -3. Between -3 and -5, we have all of the possible outcomes. We know that the area under this curve needs to be equal to 1. We know that the width here is equal to 8, so the height must be equal to 1/8 in order to make the area under the curve 1. So our probability density function here is 1/8, and that's for -3 is less than or equal to x, which is less than or equal to 5. And then for x greater than 5, there's a 0 probability of it occurring because the x is only defined on the range -3 to 5. So our probability density function here is 0. Now we can use this to find the expectation and the variance of x. Now remember, the expectation of x for a continuous random variable is equal to the integral over the full range that x can take of the individual outcomes of x times by the probability density function. Now we're going to need to split this into three parts: the part between -∞ and -3, where the probability density function is 0, the part between -3 and 5, where the probability density function is equal to 1/8, and the part greater than 5, where the probability density function is 0 again. So we can write our integral as being the integral between -∞ and -3 of x times by our probability density function, which is just 0 here, plus the integral between -3 and 5 of x times by our probability density function, which is just 1/8. So that's going to be x over 8 dx, plus the integral between 5 and infinity of x times by 0 dx, and these two parts where we're multiplying the x by 0 are going to vanish because the integral of 0 is just 0. So this is going to be equal to the integral between -3 and 5 of x over 8 dx. The integral of x over 8 dx is going to be, we raise the power of x by 1, so that's going to be x squared. We divide through by the new power, so that's going to be x squared over 16 evaluated between 5 and -3, which is going to be equal to, if we substitute in x is equal to 5, we get this is equal to 25 over 16. We substitute in -3. -3 squared is 9, so it's 9 over 16. We end up with this is equal to 16 over 16, or 1. And that shouldn't be a surprise, because remember, for a symmetric distribution, the expected value is always in the middle of the distribution. So our expected value here is 1, which is right in the middle of our distribution. In order to find the variance, remember that the variance is just equal to the expectation of x squared minus the expectation of x all squared. Now we know that the expectation of x is equal to 1, so the expectation of x squared is going to be equal to 1 squared. We just need to find this expectation, or the average value of x squared. So we can find the expectation of x squared by using exactly the same trick as we did before. Instead of now multiplying our probability density function by x, we multiply it now by x squared. So this is going to be equal to the integral between minus infinity and infinity of x squared times by our probability density function, and we'll split that up into three parts, just as we did before. The integral between minus infinity and minus 3 of x squared times by 0, which will just be equal to 0, plus the integral between minus 3 and 5 of x squared times by our probability density function, which is 1/8, so it'll be x squared over 8 dx, plus the integral between 5 and infinity of x squared times by 0 dx. Again, these two parts disappear, leaving us just with the integral between minus 3 and 5 of x squared over 8, which is equal to integrating x squared. We raise the power by 1, so that's x cubed, divide through by the new power, so that's going to be x cubed over 3 times 8, or x cubed over 24, evaluated between 5 and minus 3, which is going to be equal to 125 over 24, then substituting in minus 3 cubed. Minus 3 cubed is going to be equal to minus 27, so that's going to be minus 27 over 24, or plus 27 over 24, which is equal to 152 over 24, or 19 over 3. So we now know the expectation of x, we know the expectation of x squared, and we just need to combine these to give us our variance, which is equal to the expectation of x squared minus the expectation of x all squared, which is equal to 19 over 3 minus 1 squared, which is equal to 16 over 3. So we've now shown that the expectation of this uniformly distributed random variable between minus 3 and 5 is 1, and the variance is 16 over 3. Now, the next we're going to think about what happens if we were to sample 300 observations, so 300 random observations from this population. So this is like generating 300 random numbers, each with equally likely outcomes between minus 3 and 5. And we're going to use these to construct a sample mean, x bar, which is equal to 1 over 300 times by the sum from I is equal to 1 to 300 of xi. So in other words, we're adding up all of our observations and dividing them by 300. Now, the only things that we can say with certainty about this sample mean, now there are only very few things that we can say with certainty about this sample mean. We know, for instance, because all the observations are between minus 3 and 5, that it must be the case that the sample mean also lies between minus 3 and 5. It's impossible for it to be anywhere else. It's also likely to be the case that the sample mean is somewhere close to the middle, because since these are random observations, we're likely to have roughly equal values that are less than the expected value and are greater than the expected value, and these below and above cases roughly cancel out, so we'd expect on average our sample mean would be somewhere close to the middle. But we don't know precisely what our sample mean is going to be. All that we know is it will be somewhere between minus 3 and 5, and if we did this a large number of times, most of the time it would be close to the middle. Now, we might be interested in calculating the expected value of x bar and the variance of x bar. So in other words, if we carried out this experiment a very large number of times, the expected value of x bar would tell us the average of all of these sample means, and the variance of x bar would tell us about how much variation we'd expect to get. In order to analyze this, let's think about the sample mean more generally. So let's suppose that we sample n observations from any random distribution, and we find our sample mean. Now I'm going to start with a few assumptions. Let's start by saying that the xi, all of the observations, are independent and identically distributed. And what that means is that if they're independent, it follows that the covariance between xi and xj is going to be equal to 0. If one observation is particularly large, it doesn't influence the likelihood of another being particularly large or particularly small, for instance. Knowing the value of one outcome isn't going to impact on the values that the other outcomes take. It's also the case with the identically distributed that the expectation of xi is going to be equal to the expectation of x for all observations. So in other words, each observation has the same expected value, and that's equal to the expected value of the underlying random variable, and also the variance of xi is equal to the variance of x, which we'll denote as sigma squared x for all observations. Now, in order to find the expected value of x bar, we're going to take the expected value of x bar, which is just the same as the expectation of 1 over n times by the sum from I is equal to 1 to n of xi. Now, we know a number of rules related to expectations. The first rule that we know is that the expectation of any constant times by a random variable is equal to that constant times by the expectation. So we can rewrite our initial expectation here by taking the 1 over n outside, which is going to be equal to 1 over n times by the expectation of the sum of all of the xi's. Now, the second thing that we know about random variables is that the expectation of a sum of random variables is equal to the sum of the expectations. Now, all that we've got here is the expectation of a sum of xi's. Each of the xi's are themselves random variables, so this is going to be the same as the sum of the expectations of the random variables. So this is going to be 1 over n times by the sum from I is equal to 1 to n of the expectation of the xi's. But we know from our assumption above that the expectation of xi is equal to the expectation of x for all I. So this is going to be equal to 1 over n times by the sum of the expectations of x, but that's expectation of x is a constant, so we've got the sum of n constants, so that's going to be equal to n lots of the expectation of x, which is equal to n over n times by the expectation of x. Those n's cancel, which just gives us equal to the expectation of x. So the expected value of our sample mean is the same as the expected value of x. So we can use that straight away to write down that if our observations are IID, we know the expectation of x in this case is 1, so the expectation of x bar, the average of all of those sample means, would also be equal to 1. Now, what about the variance of the sample mean? We're going to start with the same assumptions, that is that the observations are IID. We're going to use the same sample mean, and we're going to try and find the variance of x bar, which is the same as the variance of 1 over n times by the sum of the xi's. Now, we've got a constant multiplied by a random variable, and we're taking the variance of that, and we need to use some rules relating to variances. And the first rule that we have is that the variance of any constant multiplied by a random variable is equal to that constant squared times by the variance of the random variable. So we can take this 1 over n outside, and that will be give us that the variance of x bar is the same as 1 over n squared times by the variance of the sum of the xi's. The next rule of variances that we're going to use is the variance of a sum of random variables. So if you're looking at the variance of x plus y, for instance, this is equal to the variance of x plus the variance of y, and then you need to take account of all of the possible cross product terms. It's 2 times by the covariance between x and y. Now we're going to use this idea in order to write down the variance of the sum of the xi's. So this is going to be equal to 1 over n squared times by the variance of x1 plus the variance of x2 plus the variance of x3 plus the variance of x4 all the way up to xn, plus all of the covariance terms. So the covariance between x1 and x2, the covariance between x1 and x3, and so on. And we can write that as being equal to the sum from I is equal to 1 to n of all of the variance terms plus 2 lots of the sum from I is equal to 1 to n minus 1 of the sum from j is equal to I plus 1 to n of the covariance between xi and xj. And all this term is doing, this summation here, is taking account of all of the possible cross product terms. So the covariance between x1 and x2, the covariance between x1 and x3, the covariance between x1 and x4, and so on. But because all of the observations are IID, because we've assumed that they're IID, the covariance term we're assuming is equal to 0. So these terms here disappear. So we're left with that the variance of x bar, provided the observations are IID, is 1 over n squared times by the sum from I is equal to 1 to n of the variance of xi. But we've also got the assumption that since the xi are IID, the variance of xi is fixed as sigma squared x, or the variance of x. So we've got the sum of some constant, we've got n lots of the sigma squared x. So this is 1 over n squared times by n lots of the variance of x, which is equal to, one of the n's cancel, which is equal to the variance of x divided by the number of observations. So if we now apply that to our example, we've got 300 observations, so the variance of x bar is going to be equal to the variance of x, which we had was equal to 16 over 3, divided by the number of observations, which was 300. So our variance of the sample mean is going to be 16 over 900, or 4 over 225. The key assumption that we've made is that the observations are all IID, and if they're IID, remember the key things that happen are that the covariance between the observations is equal to 0, the expectation of all of the observations is equal to some constant, which is equal to the population expectation, and that the variance of the observations is equal to some constant sigma squared x, which is the variance of the underlying population random variable. The intuition behind this variance of the x bar is this is telling us about how much the sample mean varies between different samples.